Today, we're going to learn about limits. In particular, we're going to take the notion of a limit that we understand intuitively. That means as an x value approaches a constant, the functional value approaches another constant, and we're going to make it mathematically rigorous. So we're going to write that limit definition using only for alls and there exists and a few variables that we have to instantiate. Now, to understand where the limit definition is coming from, we need to remember what our intuition is about limits. So the idea is when x is close to 3, 2 times x is going to be close to 6. So if x is close to 3, then 2 times x is close to 6. For example, if x is 3.1, 2 times x is 6.2. As I get closer to 3, 3.01, 2 times x gets closer to 6, 6.02. And that works whether or not I'm slightly bigger than 3 or maybe slightly smaller than 3. 2.99 doubles to 5.98. So as I plug in values which are closer to 3, the value of the function that I get is going to be close to 6. So what I need are variables to measure how close is x to 3, how close is 2 times x to 6. And I'm going to use delta, which looks kind of like this, Greek letter, lowercase. And what that does is it measures how close x is to 3. So what I'm going to say is that x has to be between 3 plus delta and 3 minus delta. And you can see that as I make delta smaller, x is getting closer and closer to 3. Now, in order to measure how close 2x is to 6, I'm going to use another Greek letter, epsilon. So this guy is delta, and this guy is epsilon. And what I'm going to require is that 2x is going to need to be between 6 plus epsilon and 6 minus epsilon. Now, of course, I can also write this by subtracting 3 from all sides of this equation. That tells me that negative delta is less than or equal to negative 3 is less than delta. And here, if I subtract 6 from all sides, I get negative epsilon is less than 2x minus 6 is less than epsilon. And I can also write that using absolute values. So if negative delta is less than x minus 3 is less than delta, that's the same as saying that the absolute value of x minus 3 is less than delta. And this statement is the same as saying that the absolute value of 2x minus 6 is less than epsilon. Okay, so here's the general idea. If I have a function, and I believe that that function, I'll draw it in blue here, that when I pick a value of x which is close to a, then I want the value of the function at some point x near a to be close to L. In this case, if I pick x near 3, I want 2 times x to be near 6. And how close is close? Well, I want the function value to be between L plus epsilon and L minus epsilon. So I want to pick an x close enough to a such that no matter what x I pick, I get a function value which falls between L minus epsilon and L plus epsilon. And how close is close to A? Well, I want it between A minus delta and A plus delta. So if I pick any x value in here and I project it upwards and then over, I want all of those values to fall between L minus epsilon and L plus epsilon, no matter how small I make epsilon. So how can I say that mathematically? How can I say that logically, using our for all and our there exists? Well, first I'm going to write it in words, then I'm going to write it using the math notation. So what I want is, no matter what epsilon greater than 0 I pick, I want to find a delta greater than 0 such that if x minus a is less than delta, and in this case x equals 3 for our problem, then 2x minus 6 is less than epsilon. So in other words, no matter how tight I want my function values to be around L, there has to be some tightness around x, such that no matter what number I pick, it gets sent into that narrow region around L. Now, this, by the way, was for limit as x approaches 3 of 2x equals 6. What if I want to write this statement, but just for limit as x approaches a of f of x equals L? So what I'm saying is I want x to be close to a, where delta is measuring how close x is to a, then f of x minus L should be less than epsilon. So I'm letting epsilon measure how close the function value is to my L value. Okay, so this was written down using words. The problem with words is that they can be a little bit ambiguous at times. It's best to write things in pure mathematical notation, if it's possible to do so. So let's see if we can do that. This is the definition of a limit of a function. I'll use this board over here. So, I've got a function f, which takes elements of A and returns elements of B. Then the limit of f of x as x approaches A is L. What does that statement mean? It means that no matter how tight I want this bound around L, in other words, no matter how small an epsilon I pick, so this is going to have to hold for all epsilon greater than 0. It has to hold for epsilon 0.1 and 0.01 and 0.001 and so on. It has to hold for any choice of that, epsilon. I can find a delta. Now remember, I picked epsilon first, so delta can depend on the value of epsilon, such that for all x in big A, so for all x that my function is acting on, if x minus a is at most delta, then I want my function value, f of x minus L to be the difference to be at most epsilon in absolute value. So this mathematical notation, this logical notation, is encapsulating this picture. Why? Why do mathematicians have to make things so complicated? Because now that we have this notation, we can actually prove statements about limits. And by being able to prove things, we can really explore how far limits go. And we're going to use limits in all sorts of ways. Of course, we're going to use limits to create derivatives. We're going to use a variant of the limit idea in creating our integrals. But everything about calculus arises from statements like this, from mathematical notation. Okay, so can I put my money where my mouth is and solve the question of the day? Well, first off, I need to write this limit using logic. And what that really means is I need to identify what is A, what is f of x, what is L. Because that's different from problem to problem. So, in the question of the day, I have the limit as x approaches 3 of 2x equals 6. Much better. So that 6 is my L. 2x is my f of x. And 3 is my A. So when I want to write a limit statement logically, I would say that this is equivalent to, for all epsilon greater than 0, there exists a delta such that for all x with x minus 3 less than delta, absolute value of 2x minus 6 is less than epsilon. So that's how we write this specific problem logically. And now that we've written it logically, we turn around and use what we know about how to prove logical statements. To prove this logical statement, what do? First step is always instantiate your quantifiers. So, first line of my proof, because this is a for all statement, it gets turned into a let. So I have let epsilon be greater than 0. Now, because this is a there exists, I get to choose what delta is. And my delta can be any function of epsilon. I can do epsilon squared, epsilon to the 1/3, sine of epsilon if I wanted to do such a thing. I can make delta any function of epsilon. Delta could be 4. It might not depend on epsilon at all. That's still a function of epsilon. My next statement, however, is a for all. So I have to let x be such that absolute value of x minus 3 is less than delta. And it's usually helpful, usually but not always, to write that in terms of inequalities rather than equalities, rather than the absolute value. So I'm going to get rid of the absolute value in the same way that we did earlier, by just saying, well, if absolute value of x minus 3 is the most delta, that means x minus 3 is between delta and negative delta. So far, I haven't done any thinking at all. I haven't had to think, because all I've been doing is applying our rules for instantiating quantifiers. The very last thing, what do I want to get to? That's going to be the final line of my proof. Then negative epsilon is between 2x minus 6 and positive epsilon. So how do I get from here to here? Well, it might be helpful to do some side work. I want to get from x minus 3 less than delta greater than negative delta to 2x minus 6 less than epsilon less than negative epsilon. What's the relationship between x minus 3 and 2x minus 6? Well, 2x minus 6 is just twice x minus 3, right? So if I take this inequality here, this set of inequalities, and I multiply it by 2, I get 2x minus 6 is at most 2 delta and is at least negative 2 delta. Okay, that looks promising. That does look promising. I've gotten down to my 2x minus 6, smaller than something and larger than something. But this symbol, 2 delta and epsilon, I don't know the relationship at this point. But I get to pick delta. I can pick delta to be anything I want. Can I pick delta? Can I choose delta so that 2 delta is at most epsilon? And negative 2 delta is at least negative epsilon. Well, yeah. Delta equals epsilon over 2. If I let delta equal epsilon over 2, then 2 times delta equals epsilon. What does that mean? That means that everywhere there's a 2 delta, I can replace it with an epsilon. So now I'm going to use that power to choose delta that I was saving earlier. And I'm going to say, let delta be epsilon over 2. Okay, so at this point, now I'm back inside my proof. I have to get from here down to here. Everywhere I see an epsilon, I'm just going to replace it. Sorry, everywhere I see a delta, I'm just going to replace it with an epsilon over 2. So I don't forget to do that. That's what algebra is all about. Replacing some symbols with other symbols that are equal according to some relationship. And now it's clear. All I need to do is multiply all 3 parts of this inequality by 2. So multiply by 2, and then this holds. So I'm done. That's all there was to it. Once I transformed the limit into a logical statement, then I can tackle the logical statement. Okay, so that is how you do these sorts of limit proofs. This is sometimes known as the epsilon-delta definition of a limit because we use the epsilon to measure the distance the function is away from the limit, and delta to measure how far away the x value is from its constant.